Great. So thanks everyone for coming. Today I'll be talking about forecasting of DRs for distribution operations. My name is David Larson from EPRI. I work in our grid operations and planning group, focusing mostly on forecasting. So if you work in forecasting with EPRI, you'll probably see my face. Just want to acknowledge that this is the work of multiple people on my team, including Mobalashi Bello and myself, Miguel Hernandez, Jared Green, and Lindsay Rogers. There are others that are involved, but want to highlight these as sort of our main contributors. And also I should mention, what I'll be discussing today is based on some work we've done through a NYSERDA project. We're continuing to do work with other utilities, but this has really been led off by this NYSERDA work. And the reason we're talking about forecasting, or really where the motivation is coming from this, is the fact that for most distribution utilities, they'll have visibility of their net load, obviously from SCADA or AMI devices. That's not really the challenge. The challenge is they tend to lack telemetry for DR production, particularly for the smaller DRs, but sometimes even the larger ones. And part of this is that that's a problem by itself, but it's becoming exacerbated as we continue to see increased growth and even accelerated growth in DRs. And part of this also, when I mention about small DRs, is that yes, by themselves individually, they don't have much of an impact, but when you start aggregating them up, you start having this larger and larger impact. And depending on the utility, they may be facing the fact that they're actually just getting a lot of small DR, but they're getting so many of those that that's the challenge versus just a few larger ones. Now, the question is, if you lack this visibility, it can have different impacts. And so what are some ways to deal with that? And before I get into forecasting and how that can help, the main thing is there are different benefits to having that visibility. There's things like just improved situational awareness. There can also be better outcomes for certain actions. We do things like FLISR or volt-var optimization. And so part of this is that there is a need and there's going to continue to be a need. So we want to push in its direction. But of course, the question is, how do you do this in a way that is cost effective and scalable? One option is just put sensors on everything. And that may work. That comes with a cost, both in terms of just the hardware, but also the infrastructure. And so the question is, are there alternatives that maybe we can start using today that aren't a 20-year pipe dream that needs new research? It's more of let's apply the tools we have. And so what I'm going to talk about a little bit, and there's many things I could touch on for this, but to keep it under time, I'm going to focus on a few key details. Please come talk to me if you're interested in this topic. But for most utilities today, at least in the US, the DRs that they're dealing with primarily or they're most concerned about are behind the meter solar. That's going to be changing over time, but that's really what most people are focusing on. Now, the good part is forecasting exists and it's a very mature technology for solar. And so there's things we can adopt. It's not I need to start this massive research initiative and spend 10 years before I get results. There's years of success in transmission. These forecast methods are also commercially available. So it's not just you're a research lab and you have to figure out how do I get this out to industry. These ones also can be scalable, and there are methods that require minimal data dependencies. So if you don't have measurements, you can still start getting forecasts and use those as a proxy. Just a big picture of one approach that you can take for this, particularly if you don't have any measurement data. If you at least have information about what PV is installed, its location, at least its nameplate capacity, though other information like tilt and orientation can help, you can do things like take gridded solar radiance forecasts, which are produced by a number of different methods as well as commercial providers. And just with those two pieces of information, you can start getting solar power forecasts for those PV. Now, without measurement data, it's not going to be perfect, but this is something that's practical that you can adopt today. And you can also get support from this. So if you're a utility or an IESO that needs this today and needs it from a commercial vendor, those exist. EPRI's worked with many of them. And if you've worked with us before, you know that EPRI is not a forecast provider, but we work closely with those that end up providing these forecasts. So this is a simple idea. It is something that you can put into practice today. There are other methods that are more advanced, but this is something that everyone could start doing today, given they have some information about their PV. There are trade-offs if you don't have all that information, but this is something you could start adopting. I want to talk a little bit, some key takeaways from a study we did in New York State with the distribution utility. For this, we had a very nice setup, and I'm just going to focus on a few key details, but we did a lot in this project, and there's enough time to go through everything, but I can talk through a lot of it if folks are interested after. So for this utility had already done a campaign where they installed separate meters to give direct measurements of PV production from behind the meter solar. So they didn't do it for all sites, but within a sub-region of their territory, they had 15-minute data for about 2 years of each of these. This wasn't estimated, this was directly measured. And so for this, we actually worked with a commercial forecast provider so we could actually kind of get a sense for what could you do today with this result. And we looked at everything from sort of a nowcast horizon, which would be more of estimating what is not exactly your real-time production, but pretty close to that, to also 7 days ahead to sort of understand what are the trade-offs, what can you do today with this. We also did a lot with load forecasting, and we also did a lot with applications of using these forecasts for distribution operations, but I won't have time to get into all of that. Going to do a couple of key takeaways, which some of these may seem obvious to you if you've done forecasting before, but it's always good to test these in new situations where you don't have data yet. So one of these we looked at, and part of this also for the distribution operators is forecasting for some of them can be a newer concept. And so sometimes there's this piece of sort of more education to understand what is possible. And one key part that we find sometimes is understanding that there are many different variables can impact forecast accuracy. If you say I have an 8% error forecast model, that doesn't mean every single hour of the day is 8%. You could have some periods that are much more accurate, and then you have a few periods that you really miss the forecast so that your average error is much higher. But in this one, we were actually able to look at things like, what if you forecast the individual behind the meter PV? That is possible. There's an open question of, do you actually want to do that? But you can. There's benefits when you aggregate these to a feeder level or a larger aggregation. We've seen that before with many different types of forecasts. But again, this is good to sort of just confirm. And then with this also, you're concerned, of course, about absolute accuracy, but also bias. Because if you're over predicting and you end up having less solar come online, that's a very different proposition than the opposite. So this is just one of the results. And as I'll mention at the end, we have a couple of public white papers that you can read more about this work. Another one that comes up is there's the question of, well, if I do forecast, does that mean I no longer need telemetry, or vice versa? And what we are able to show through this case study, at least, is that even if you have measurement data from a few locations, you can still get a benefit on your forecasts. And so this was one example where we actually varied the number of locations. So we had data for all locations. And what we varied is we randomly picked a subset of those through a bootstrap method to evaluate if you have measurement from a few locations, could you improve your forecast? And this was also a thing that you could definitely, if you have live telemetry from these locations, do it in a rolling basis. It could also just be a historical setup. And so generally what we found is, to an extent, if you have more measurement data, you can improve your forecasts, but there is sort of a limit to that benefit. But this is an interesting result we felt, and it's something that points to the fact that you may go to a hybrid method where you have telemetry on some locations, but maybe not all, or maybe you're moving towards having telemetry on all locations, but you can start seeing benefits even with a few locations. Now, this was for one utility. We are doing additional work with others to try to demonstrate this more generally, but we think this is a key takeaway from this work. The last thing I want to bring up is for distribution operations today, at least, for forecasting, there isn't such a clear-cut application. There isn't things like a day-ahead market where you're required to have a forecast. And so part of this project was looking at what are different ways you can benefit from forecasts and what are those gonna provide you. So one thing we did in this project, which I'm kind of skimming over the details, is we actually worked with them to develop an open DSS circuit level model for part of their territory. And for this, we used the forecast to try to see if we could use that to identify issues ahead of time. And then we would compare it to the real time. So in this example, this is a nice one to illustrate where actually using that day ahead forecast, we were indicating that there was going to be a thermal limit in part of that circuit. And then when we went to the real-time data, we actually observed that thermal limit. So this idea of situational awareness, not just being what's going to happen in the next hour, but actually starting to think about maybe more of an operational planning mindset, where you could look a little bit further ahead, you could plan out things. We did similar applications for things like battery dispatch, for hosting capacity, as well as volt-var optimization. So there's open questions about how best to use the forecast and the sort of what is really going to be the selling point to adopting forecasting. But this work kind of led the way that this is possible with technology we have today. There's still open questions, but we're moving in the right direction and we can leverage things that we already have. A couple of quick notes about this, sort of where do we go from here? Like I mentioned, there's open questions about how best to integrate this, what sort of forecasts are needed, where are the applications where you want to use forecast data versus measurements. There's open questions about, well, do you go with a full in on all sensors? What about all forecasts? Or do you maybe go to some hybrid middle ground where you say, I have sensors on some locations, and maybe I use forecasts with that measurement data to get a better result. There's also, of course, questions. I didn't talk about other types of DR. Now with solar, it's very nice. That's a weather-driven technology, but it's well understood. There's lots of physical basis that you can go from this. You don't need measurement data. Other DRs are much more user-driven, and so it seems to be that for other DRs, you would need some type of data. There are open questions there about how well you can do. Now, there's a lot of work in different regions for other types of DR, but at least for solar, we have something to go on, and probably these other types of DRs will become kind of the next big challenge. Last thing I'll mention is just we've had topics especially in the transmission side about probabilistic forecasts. There are questions about how could you leverage that in distribution. It seems like at first you just want to get onto the forecasting mindset and using that, and then you can build upon that to get to probabilistic. But I think there are going to be use cases for using probabilistic on the distribution side as well. It's just a little bit early on with this. The things I'll end with, and I'll leave these up for a bit, we have 2 public white papers on this work. So I've put up the QR codes if you want to try to scan those, but when the slides are shared later, you can also get those. There's also the EPRI product ID. And so these touch on sort of the main details from this. They're meant to be shorter white papers, so they don't get in all the details, but these can be a great way to introduce the topic and get conversations going, especially if this is a topic that you need to converse with, for example, senior leadership at your organization. These could be ways to sort of high level, what are some of the initial results that we can work on? And then the thing I'll end with is about part of this is understanding how well do these forecasts perform and how do we assess them and what are the things we need to be focusing on that maybe are similar or different to transmission. And so one thing that EPRI has been doing a lot more on is this forecast arbiter tool, which is much more on the assessment of forecasts and giving that information back to users to understand what are my forecasts performing like? How is that impacting my results? What are the areas that I need to maybe work on? So this is an existing open source tool. We're using this for a lot of work, things like the American-made net load forecasting challenge, where we're doing probabilistic substation level forecasts in a competition with prize money. We're also doing forecast trials with a lot of the vendors. So you'll probably see more of this from EPRI, but we think it's important of not just getting the forecast, but understanding how it performs and what that means for your operations and bringing that to a full circle of not just, cool, I got a forecast, my job is done. Understanding, where are those pain points? Also, where should the research go? And just generally, what is available today that you can start using? So I'll end with that. Thank you very much for the time, and I look forward to questions.
Thank you, David. And very much want to echo your second takeaway as well. We've had some really effective results, actually upsampling some small system data to validate our visibility. So I think that's really good. Yeah. Oh, sorry. I'm going to introduce Ali to talk about Yeah, using transmission, distribution, coordination efforts. So yeah.
Hi, everyone. Pleasure to be here. I'm Ali Golriz from the IESO. I work in the innovation team there, specifically on DER integration and with a focus on the TD interface and coordination. I'm going to be talking about a DSO pilot that we have and describe how we're thinking about sort of operations in terms of distribution services, wholesale services, coordination, different models, and going to touch a little bit on what that may mean for forecasting. Just really quickly, in terms of the IESO, we are the system operator in Ontario, Canada. We administer a $20 billion a year market. We do bulk planning, but interestingly, we also do regional planning, so a little bit different from other ISO RTOs, where we get a little bit more granular. We support innovation, including pilot projects like the one I'm going to speak to. And engagement is core to what we do. We also design and run programs, again, a little bit different from other ISO RTOs across North America. To give you a sense of Ontario and the ISO, our installed capacity is about 40 gigawatts. We peaked somewhere in the range of 25 gigawatts. We have 5 million retail customers. We're connected to our neighboring jurisdictions. The demonstration project, and my presentation is going to be sort of grounded in this. It's funded by NRCan, Natural Resources Canada, and the IESO, and Electro Utility is one of the progressive sort of distributors in Ontario as our delivery partner. And what's interesting about this is that there's sort of federal, provincial, and local support and involvement in this project. The objective of the project was really to contribute to distribution markets and the thinking there, as well as transmission distribution coordination. And so what we did in the project is that we designed and implemented a number of auctions and services, local ones at the distribution level. And it was sort of inspired by wholesale mechanisms. So we have a capacity and energy and a reserve service in the demonstration. And really the intent of that was for the distributor to use those to manage a non-wires project. To give you a little bit of a sense of sort of how this all played out, we ran 2 capacity auctions, one for 10 megawatts of DR capacity, one for 15 in 2020, November 2020, and again in November 2021. And so the folks that sort of cleared in that, the intent was that they are then have a must-offer obligation, so they have to be available in energy and reserve auctions, again, local ones. And so we ran those energy and reserve auctions from May to October, sort of the summer half of the year. And yeah, we had up to 10 sort of events, and that's sort of how we approached that. What was interesting in the demonstration is that the reliability needs were simulated, but everything else was real, including the dollars. And our sort of focus in the project was on not solar and sort of passive resources, but dispatchable resources. And we saw great sort of participation in the project, in the sense that we got a range of different participants, including an aggregation of smart thermostats, aggregation of behind-the-meter batteries, gas engines, load curtailment, even a CHP plant that was providing district energy services. So what I'm going to do in this presentation is there's a lot going on in this demonstration. I'm going to focus in on the energy service, the coordination approach, and speak a little bit about the forecasting again. Give you a sense of the project, just the activities in it. We started 5 years ago. We worked with consultants, primarily ICF and EPRI, and we also spent a lot of time with lawyers developing rules and contracts for the demonstration. We also built a web-based platform. So this is to manage and administer the sort of local auctions in the demonstration. So the registration, the actual auctions, and all of that. And right now we're in the final stages of the project. We're sort of wrapping up, doing a number of reports and studies. So in terms of the energy auction, and again, there were a number of services, but I just want to focus on the energy bit here. The way we structured this, and we again borrowed from the wholesale services where there's something similar that the IESO does. But the way we sort of structured this is that the distributor, Electra, would, before 7 a.m. in the morning, do a quick check in terms of their load forecast and where they expect the day to go. By 7 a.m., they would have to provide a standby notice to the participants in the demonstration. And then 2 hours before the actual event, an activation notice would be sent. And then we could operate the DER up to 4 hours. What's interesting about this is just the timing. From a forecasting perspective, the distributor needs to have a fairly rigorous forecast, but also the activation notice and the 2 hour in advance sort of time frame for that lines up with when the IESOs, the wholesale market gate closure happens. And that to me is sort of a key piece to the puzzle in terms of visibility and seeing what the distributor is doing. And I'm going to describe that a little bit further. So that was sort of the process for the energy service. This is the need. So this is from Electra's perspective, the distributor perspective, and what was going on there. And I'm going to sort of note a few non-wires thoughts here as well. In particular, the way we were coming at this, we were sort of anticipating that there's going to be congestions at the distribution level. So the demonstration was in a suburban area, York region. All the DER had to be located there. There's our planners, ours and Electra's planners, anticipate that there's going to be new stations, but also a large transmission solution in that area. None of that has materialized. It's sort of forthcoming needs, but we wanted to ground the project in reality. So what we did is that we simulated a threshold, basically a limit. And we said, whenever the forecast indicates that the load in that area, in that pocket, where potentially in the future there could be congestions, whenever that load exceeds a certain threshold, the limit, then there's an activation in terms of local energy, local reserves, and the auction processes sort of play out, and we direct DER operations. So that's how we came at that. And I'm going to switch gears a little bit and tell you about coordination, and I'm slowly going to work towards sort of forecasting and what happens at the TD interface. This is a framework. It comes from Lorenzo Christoph and Paul DeMartini and JD Taft. We've worked with Lorenzo and Paul. Their framework, my commentary, I suppose. So this is about DSO models and how distribution and transmission to wholesale could be structured in the future. They describe sort of a range of potential ways of going about it with 2 bookends and a whole bunch of ways of slicing and dicing things in the middle. So in terms of the total ISO or the total TSO, basically means that the ISO gets visibility into the distribution system, manages all the services. If there are congestions, we would do that. There's a range of issues with this, jurisdictional challenges, FERC state divide sort of here in the US, issues in Canada. Tools don't exist. There's scalability issues. So that's sort of that model. On the other side of the spectrum, there's a total DSO, and that's characterized by there being one interface for the DER, that being the DSO, the distribution system operator, who then in turn interacts with the ISO. The ISO dispatches the DSO disaggregates down to the DER. So I think of this model as a sort of a super aggregator. The DSO would be a super aggregator, potentially aggregating other aggregators. Another way to think about it is that it's sort of a regulatory aggregator, where there's, the regulator would sort of establish how that would work. There'd be transparency in terms of how the DSO sort of aggregates the DER and takes care of all that. In between, again, a number of ways of going about it. One that I really like is, we're calling it the dual participation, sort of borrowing from New York, is that the DER go to the ISO for wholesale services, goes to the DSO for distribution services. There's many ways of doing this. Another one is, if the DER is providing distribution services, then the DSO becomes the aggregator. Otherwise, the DER goes straight to the ISO. Another version is, residential, very small DER, get aggregated by the DSO. Everybody else comes directly to the ISO. So that's sort of the landscape. Key in all of this is observability into, again, dispatchable DER and what's happening at the TD interface. And we're working with EPRI. This is not published yet, but we're developing a report and a study. on all of these issues, and we're working through different coordination protocols, getting into the details of that. And again, I think the key here is advanced visibility. So getting a sense of what the distributor is going to do in terms of distribution services and capturing that in market bids and offers. And I'm in the next slide going to show you how sort of we were approaching that. Also in terms of coordination override, in terms of reliability, the distributor can stop the IESO's dispatch and schedules. And then, oh yeah, I touched on this a little bit. The mechanism for getting that advanced visibility is reflecting what the distributor is doing in wholesale bids and offers, and doing that by submitting, must operate or price taker offers or something along those lines. Somehow it needs to be identified that the distributor is requiring the DER to operate. So this is a slide that I borrowed or stole from EPRI and the work that they're doing for us, but it's a great way of sort of showing how the process unfolds that we're envisioning. And there's a deliberate order here. So first, the distributor identifies distribution needs and schedules the DER for that. Then there's the wholesale market offers that need to be structured. That's submitted to the IESO. We clear the market, we dispatch down, and the dispatch is disaggregated down to the DER. Depending on the model that's adopted, that the structuring of the wholesale offers may come from a third-party DER aggregator, or it may come from the DSO. And then similarly, when the IESO is dispatching, it may be dispatching the third-party DER aggregator under certain models, or it could be the DSO that's being dispatched. Contingency management is also on this slide in terms of override again. So that's another process, and they've sort of identified the M&V and settlement on here too. Drawing more from the work that EPRI did for us. So we've been thinking about sort of different cases that need to be thought through with respect to forecasting. And EPRI in detail stepped through 8 different cases for us to identify what's being seen and what needs to be forecasted, and sort of looking at the conclusions here. But in terms of observability or visibility, the IESO can see what's happening at the TD interface and also the DER that are participating in our markets. So to the extent that they're stacking and the DER doing both distribution services and wholesale services, we would see all of that, and it would be sort of embedded in our market bids and offers, and our tools and systems can capture that. But to the extent that the DER is only providing distribution services, we do not have visibility. And of course, we don't have visibility on what we call non-dispatchable loads, or loads that are not participating in the market. Another piece to the puzzle is that we already require in Ontario that distributors notify us if there's going to be material deviations to the forecast. So if there's something unplanned going on, unexpected going on, we expect that there's going to be a notice. So that's in terms of what we have visibility into, and then under the forecasting bit. So our forecast already captures non-dispatchable loads, and we break it down into TD interfaces using distribution factors. And to the extent that the DER are not participating in our, or are participating in our wholesale market, then they're not embedded in the load forecast, but the DER that are only providing distribution services are embedded in the load forecast. So that's sort of the initial assessment of what we have going on at the IESO and where things could go. But I also wanted to, and EPRI did a assessment of all of this for us to see, if the mechanisms that we have in place already capture the needs. And they noted that, given the IESO's existing forecasting approach, taking things down to the TD interface, given the bidding mechanism or that sort of advanced visibility where we see what the distribution services are, and that's embedded in the wholesale bids and offers, and that notice that the distributor needs to provide to us when there's something unexpected going on at the distribution level, those 3 things in combination largely capture our needs, and we have visibility into what's going on at the distribution level. And so the final slide I wanted to to end with is that, as much as we've been working with EPRI on sort of what all of this means for forecasting, I think this is just the beginning. And there's a range of, I think, sort of parameters or dimensions that need to be thought through. And frankly, as a non-forecaster, this is a little bit overwhelming for me. But I think the forecasting approach changes depending on the model that's adopted. Also, in terms of dispatchability of the resources, the time frame of the forecast, whether the DER is providing distribution services, both distribution and wholesale services, no services, what that looks like, and then congestions in the distribution system, what that means for the TD interface, what we see at the TD interface, the impact that's there. And then finally, I think we need to step through different sort of scenarios in terms of planned and unplanned conditions, abnormal conditions. And with that, I'll pass it over to the next presenter. Thank you.
Thank you, Ali. I think it's so important and vital that we have more collaboration between ISOs and distributors as we continue to adopt DER. So that's a really good use case to see. I'm going to invite Jared next. I'm going to talk about bulk systems operations.
All right, good morning, everyone. My name is Jared Lee. I'm a project scientist at the Research Applications Lab just up the road at NCAR, the National Center for Atmospheric Research. Before I begin, I'd also like to acknowledge the co-authors on this presentation, Susan Detling, Julia Pearson, Tom Brummett, and David Larson. So as most of us know in the room, several states around the country have pretty aggressive clean energy standards. New York is no exception. They're targeting 70% renewable generation by 2030 and 100% by 2040. So New York needs to be installing a lot more clean energy, including solar. So accurate forecasting is becoming more and more critical for utilities and ISOs like New York ISO, both for intraday and day ahead, for both utility scale and distributed PV sites here. And so this was part of a project that was funded by both NYSERDA and NYPA with a team of several entities here. So to just describe what we call the New York Solarcast or NY Solarcast system, it has observations coming in from the New York State Mesonet. I'll talk about that in a little bit. Also some numerical weather prediction data from the WRF solar model and HER. We have machine learning where we train on multiple years of data from the New York State Mesonet and the models. We blend those together into a gridded background forecast, and then use the most recent New York State Mesonet observations to correct that forecast, and then we spread that correction out into the grid. Then we have additional machine learning where we train. It's very sensitive. Additional machine learning where we train on historical power data, and all the data that we have from both the utility and distributed sites was historical only. We had no real-time data. And out of that, at the bottom is then both utility and distributed percent power forecasts. And so we issue these forecasts every 15 minutes throughout the day. So we have 15-minute frequency for both the GHI and the utility PV, and then 1 hour forecast for the distributed, because that matches the data that we had. Then we also issue day ahead forecasts once daily at 6 UTC, but this presentation will focus entirely on the intraday. So really critical to our system is the New York State Mesonet. So the New York State Mesonet has 126 stations across the state, these little blue dots. If you can see them, there's at least one in every county of New York. And so we got the data from the start of 2018 all the way up through middle of last year. And what's really important here is that each Mesonet site has a pyranometer. And then a subset of the sites also have a higher quality pyranometer up above. We didn't end up using that data in this project, but that would be a really useful exercise, because these pyranometers don't give the same values, and they have different calibrations. And so there also were instances of shading and snow and ice covered pyranometers. Many of those were found by the University of Albany, which manages the New York State Mesonet, and those were excluded from training and validation data sets. And also, New York State Mesonet goes around the state, replacing about 20% of their pyranometers each year. And so that brings its own challenges, that there are different standards in the measurements. So for our numerical weather prediction models, we use the WRF solar model, which was developed at NCAR to really enhance the WRF model for solar forecasts. So we issue every hour from 11 to 19 UTC. We issue these out to 6 hours for the intraday forecasts at 15-minute temporal frequency and 3-kilometer grid spacing. And then we also download the operational HER model from NOAA and then regrid that to the WRF solar grid. And then for our machine learning, we use a model called StatCast, which also we developed at NCAR. We've used in several of our other wind and solar forecasting systems that we've used. StatCast uses the QBIS machine learning algorithm, it's a decision tree model. And we have a separate model for each forecast lead time. But then for each lead time, we have just a single model for all of New York. We did test breaking it up into the different climate regions in New York, but having one model for the whole state proved to be the best. And so what QBIS actually predicts is the clearness index, which is basically a measure of how clear the sky is. And so what that does is that removes the very strong diurnal trend that we have in GHI, and we can easily convert back and forth between GHI and clearness index. And so you can see at 30-minute lead time, the most recent clearness index observations are the most important, which makes sense. And then the known solar angles are also very important. But then once you get out to a 6-hour lead time, then really the WRF solar variables take over as being the most important. Those are the blue ones here. And so our training period was 2.5 years basically. And then we have a 1-year validation period from the 1st of May, 2021 to the 30th of April, 2022. And so to blend these models, here panel A is the WRF solar forecast, panel B is the HER forecast. There are some subtle differences. We blend those together, and then by mapping the New York State Mesonet sites onto the nearest WRF solar grid point, then we're able to convert the clearness index back to GHI at these sites, and we're able to correct the grid using the machine learning that I just described, and then spread that out using different radii of influence, and that results eventually in this final gridded product here in the lower right, panel D. And gradually we relax. After about 3 hours, we start relaxing the StatCast back toward just the pure WRF solar and HER blend at 6 hours, so that it's a smooth handoff. We don't have to do that. So for the utility PV farms, so we had 2 providers, 10 farms across the state. Each farm has its own different start date, its own QC issues. Some farms are curtailed daily, some aren't. And so basically what we do is we look through the historical data and we estimate. We don't just take the nameplate capacity for its word. We look in the data at what is the actual maximum production that we see. And so we use that as the estimated actual maximum capacity. There's some really messy data. Percent power output can be really spiky at times, so we have to QC that out. So there's just a lot of data QC that has to be applied, especially to each farm. And so for the distributed sites, I'll spend a little more time on this since we're in a DER session. So NYSERDA has a database of over 101,000 distributed installations across the state, and 1-hour production data from about 500 or so representative sites, we call them. And so most of these are fairly close to a New York State Mesonet site. And so we use Mesonet observations for the weather data. And also we have a single statewide distributed percent power QBIS model. But I will also add that a lot of this data is very messy, as I'm sure most of you in this room know. real data is a challenge to work with. And so we do have to clean it up in order to get a really useful data set. And at the end, there were about 436 sites that were not just completely rejected by our different QC methods. And we did have to apply additional QC beyond what NYSERDA does. So again, you can't trust the data. You have to apply additional QC usually. And then what we do is, so for each grid point, we predict what the percent capacity power is, and then we aggregate that up into zones. So we started out by aggregating into regional zip codes, the first 3 digits of the zip code, and that is surprisingly messy for New York. Some really interesting Swiss cheese zones for the Postal Service. But also New York ISO has these New York control area load zones. Those are much cleaner. But really you can aggregate these forecasts into any zone, counties, whatever is useful for you as a utility or an ISO. And so it is a really flexible framework. And one thing I do have down here, a note that there is some mismatches that we found in the data set between what NYSERDA had in its database and New York ISO in its database. I just talked to Anthony actually right during the break before this, and I think I have a lead on what the source of that disagreement is. So thank you, Anthony. Anyway, so validating the clearness index forecast at the New York State Mesonet sites. We find that, so New York Soilcast is in blue and StatCast is in orange. Our reference forecast is a smart persistence. And we see that even at the very short lead times, our model is beating smart persistence, which is actually really difficult to do at 15 minutes. And out to 6 hours, we're beating just the background numerical weather prediction blend as well. And we can see, comparing the bias and the mean absolute error, that New York Solarcast has basically almost all the stations have a lower MAE and a lower bias than either the clearness index or the NWP blend. And looking at it as a function of time of day, again, we have pretty consistent errors throughout, except earlier in the morning and later in the afternoon, we do have a few more outlier sites. Each of these diamonds is one particular site over the whole year. And so that could indicate some additional shading, like as trees grow, the QC might need to get more and more aggressive at monitoring that. And looking at this statewide, some of our highest error sites were in the Adirondacks, like this site right here. And if you look at Google Maps, you can see that it is completely surrounded by a forest. And so we're pretty confident that shading and possibly also snow cover up there is part of why we see some sites with much higher errors. And then, so looking at our forecast of GHI at the utility sites, and again, we did not have any of this data in real time. We got monthly data deliveries after the fact. And so if we just take the NWP blend, this is our error. And so we're much better again if we use StatCast, which is in orange, at the nearest Mesonet site. But New York Solarcast beats that. So that shows that spreading out these errors from the Mesonet into the outer grid results in a better prediction. And we would be even better if we were getting any of this data in real time. So but this just shows that even if you don't have the data, New York Solarcast is adding value. And as far as power validation at these utility farms, most of them had a mean percentage error between -2% and 2%, and a mean absolute percentage error between 9% and 12%. You'll notice there was one outlier farm down here, and we're fairly certain that that's because it had a much shorter training period and also had several months of missing data during this 1-year validation period. So just kind of showing the different farms. Fairly consistent characteristics as a function of lead time. Time of day, we do notice that some of the sites follow the diurnal curve and some have more of a duck curve. And we're pretty sure that that's indicating that these sites are likely overbuilt. We don't have confirmation of that, but we can just tell that or infer that from the data. So again, now moving to the distributed sites. So we picked 10 of these representative sites from the NYSERDA database to test our validation on. These have a range of sizes, and they're all fairly large distributed resources with a range of tilt angles and azimuth angles. And we can see that there's one site in particular just north of New York City that has a much larger absolute error and mean percentage error, basically bias, than the others. And we think that that's due to having a much lower tilt angle, 10 degrees, and also an azimuth angle of 200 degrees, that it's just not representative of the rest of the distributed sites that are in that region that we use to train the model. And so we're fairly comfortable with and happy with these error forecasts or error results. And another thing that kind of dovetailing what David said earlier, when you aggregate the forecast together, which is this thick black line, we're able to reduce the absolute error to below what any of the individual sites were. So this is also similar to ensemble forecasting in numerical weather prediction, where the ensemble mean forecast is often better than, has a lower error than any of the individual ensemble members in the forecast. So it's a similar concept here. We find really the benefits of aggregating our errors instead of forecasting for individual sites. And again, none of these individual sites were specifically trained on. And so we wouldn't expect to have really perfect forecast for an individual distributed site. Again, for time of day, we see a similar thing here, just improving the total power error. But then, it's that one site just north of New York City has much larger error, and we believe that's due to different characteristics in it. And aggregation, again, just helps cancel out some of these differences in the range of different tilts and azimuth angles that you can see. So just in conclusion, the New York Solarcast system is open source. And I have the link to the GitHub repository where you can download it. And it's also configurable and applicable to other areas as well. So we produce 15-minute % power capacity at utility farms and 1 hourly at distributed PV aggregated to any customizable regions that you want. Having real-time New York State Mesonet data is really crucial to this. So you do need data coming in to have the good forecasts. But you don't necessarily need data coming in from the power, either utility or the distributed side. And so we have some ideas of how we want to continue improving the system, and in the final stages right now of preparing a manuscript for solar energy. So with that, I'll take questions at the end. Thanks.
Thank you, Jared. That was an incredibly thorough overview of that methodology. I will definitely be stealing a few things. Thank you. Okay, last but not least, we have Lars talking about congestion management.
Okay, now we come from New York to Germany, and I want to talk about the new redispatch tunnel in Germany, which is actually a process for congestion management. My name is Lars Rohwer. I'm a senior meteorologist at Energy Meteo Systems for 3 years now, and I'm in the quality assurance department for our forecasts, and also I'm responsible for our network operators in Germany and the US, so our customers there. We are actually 3 companies now. Energy Meteo Systems, most of you should know, it's for the energy forecasts all over the world, one of the leading providers. And last year I talked about the EMSIS VPP, the virtual power plant we provide. And this year it's about the EMSIS grid services. It was founded 2 years ago for this redispatch processes in Germany, and does all this grid management and load forecast, virtual grid load, flows, and anything like that. This redispatch tunnel was published in the Act in May 2019. 2019, and yeah, it has to be implemented by the grid operators by October 2021, so just 2.5 years. The main thing, so it's a German act. If I would tell you something about all of that, it's a big book, so just main things. For the first time, you have to integrate every distributed producers from 100 kilowatts into this redispatch processes. So that's are a lot of wind and solar and producers and a lot of data there. Before this, this congestion management was more or less in real time. So if the system operators saw that there will be congestions, they dispatched, shut down the plants, mostly wind power plants, and now in an optimal case, even in the day ahead, the traders and the forecasters like us know which plants will be dispatched, which plants will be shut down. So it's so the redispatch to nil is a big planning process for congestion management. You can have different steps. In EMSIS grid services, you can get the full all-inclusive package. So we do most of this redispatch things that the customers need, or you can buy or get just some modules out of it. And every redispatch to nil process starts with grid analysis, and we use our high resolution forecasts for all the plans, and then you get schedulers on and informations about consumption. So you have a status quo more or less, and then you can start and predict load flows and congestions in different variations. What this means, we can see with a deeper dive in the grid analysis and the forecasting for it. We start with this determination of the vertical load forecast at every grid node, and then with a calculation of the load flow at this grid nodes. And when we have this, we can do a predictive load flow calculation on every of these grid nodes. And we don't just do a basic case n-0, because it's more or less the important thing about it, that you do the calculation for the failure variant. So when there's a transformer not working, you can don't use a grid line. So the n-1 is quite important to get different various scenarios, so you can determine the congestion in a planning process. Another thing that will help is dynamic line rating. So you can even get this module, and with it you can increase the static grid operating limits, because it exploits the effects of the weather-dependent grid capacity. So for the capacity, it's the weather is the main thing. So and there the wind speeds. When the conductor ropes can get the maximum current carrying capacity depends on the wind speeds, and we just use our NVP weather models to calculate it. And in some regions we even have measurement data from the network operator, and this will even help us to get a good dynamic line rating. Back to the redispatch steps. If you have the forecast and the analysis, you can make an optimized redispatch dimensionizing and a plan scheduling. It's what I said, in the optimal case, you have in the day ahead and a redispatch plan for every plant. And the last thing is the market communication between all the players in the market. We will see later there are at least 900 distribution network operators in this redispatch processor. There are many players, and there's a lot of communication needed. And a new thing also is that the traders or the plant owners get a balancing, get money for when the plant is dispatched. So this balancing and accounting is also needed to do, and yes, that's another module. There are some lessons learned about the redispatch process. So as I said, there are only 900 distribution network operators in Germany. Then you have the vendors who do the different processes, and then you have the guys who are responsible for the different plans. So there are many players. Just a map of Germany where you can see the 900 distribution network operators. You don't have to read anything, but yeah, look at the different colors, and there are many different and small distribution network operators. So yeah, a problem, they don't have that much money, and you need extremely large data volumes for this redispatch process. So it's a very expensive IT infrastructure. And yeah, the 2.5 years from an act to the fully implementation is less time. It's not enough time. We have to say, even at the moment, the process isn't to 100% working. Mainly this balancing process is it's still under construction, and yeah, there are still some problems. But what we have to say is the idea behind this redispatch tunnel is good, but the implementation must be simplified if you try something else in other countries. So when you have so many stakeholders and players, it has to be hold simple, otherwise it's quite hard. So thank you.